Okay, we are on Introduction to Dynamic Equilibrium. We're going to take a look at the warm-up. It says, every weekday from 7 a.m. to 9 a.m., a big volume of traffic flows into New York as people who live in the surrounding communities drive to work. Are there any cars leaving New York between 7 and 9 a.m.? Of course there are. Explain how the number of cars in New York remains relatively constant between 10 a.m. and 2 p.m. when cars are still entering the city. Well, cars are leaving the city at the same rate. Number 3, the number of cars in New York decreases between 3 and 7 p.m. Describe the traffic flow during this period. Well, cars leave the city at a greater rate than they're entering at this time. And today we're going to be talking about reversible reactions. A lot of chemical reactions are reversible, and reversibility allows an important phenomenon known as chemical equilibrium to occur. So chemical equilibrium happens when the forward rate of a chemical reaction, where we're converting reactant to product, equals the reverse reaction rate, or we're converting product back to reactant. So if we take a look here, chemical equilibria are dynamic. That means they are actively happening. So the forward and the reverse reactions are continually occurring. And when you're producing product, the reactant is actually being put back by the reverse reaction at the same rate. So we're using up things and we're putting things back. And the consuming of reactant versus the production of reactant is continually happening. And although the concentrations of reactants and products is not necessarily the same, the concentrations should be constant, okay? The consumption and production ratios are actually provided by the coefficients in a balanced chemical reaction. So here you'll notice that we have got hydrogen reacting with oxygen to produce water. And this equation shows us that hydrogen is consumed and produced at twice the rate in moles because the coefficient is a 2 in comparison to oxygen, which has a coefficient of 1. And what we can do is we can use these coefficients to come up with the rate of consumption or the rate of production of a certain substance in a chemical reaction. So if you take a look here at this sample problem, it says nitrogen dioxide is being consumed at a rate of 0.031 moles per second in this equilibrium below. Equilibrium has double arrows in between the reactants and the products. How many moles of N2O4 are being consumed each second? Well, if this is moles per second, all I need to do is take that rate and then do a ratio from NO2 to N2O4 like they've done here using the coefficients to give me my consumption for N2O4 per second. We're going to do something like that here. So we have SO2 and O2 in a sealed flask. They're producing SO3. At equilibrium, SO3 is being produced at a rate of 0.0082 moles per second. So how many moles of SO3 are being consumed each second if we knew how much was produced? Well, the rate of consumption equals the rate of production at equilibrium. Okay, so that means that if I take my 0.0082 moles per second rate of production, that will also be the rate of consumption for SO3. Number 2, how many moles of O2 are produced in a second? Well, I need to use this rate for SO3, and I need to relate it from SO3 to O2. So I'm going to use this coefficient of 2 for SO3, and I'm going to use the coefficient of 1 for O2 here. I'm going to divide this. I'm going to get 0.0041 moles of O2 per second. Number 3 says, how many grams of O2 are consumed each second? Well, can't I convert moles to grams by using the molar mass? So we're going to take this value and I'm going to convert to grams. This number comes from the periodic table. Remember, oxygen has a molar mass of 16, so I need to multiply that by 2, and that's how I get 32. So I'm going to multiply these together. That'll give me 0.13 grams of O2 per second. Now, how do I recognize when we are at chemical equilibrium? Well, there are 3 criteria that a system needs to have. Number 1, it needs to have constant macroscopic properties. Macroscopic properties are properties that are large enough for you to measure or observe with the unaided eye. Number 2, it has to be a closed system. Number 3, it has to shift when conditions change. Let's talk about the first property, constancy of macroscopic properties. So a system that's at equilibrium is going to have constant macroscopic properties like color, pH, temperature, and pressure, because the amount of each reactant and product remains constant. So each chemical is being produced at the same rate that it's being consumed. Let's turn the page. Let's talk about a closed system. A system is closed if no chemicals are entering or leaving the system. So if a system's properties are constant, but the system is open, we call it something different. We call it a steady state. This is not equilibrium. In a steady state, you have things entering and leaving the system at the same rate, rather than going back and forth like they are in equilibrium between the reactant and the product. So a steady state exists when the water level behind a dam stays constant because water is flowing into the lake behind the dam at the same rate that it's flowing through the dam, okay? Aqueous solutions will only achieve equilibrium if all the reactant particles and product particles and the solvent water molecules remain in the solution. If an equilibrium is temporarily disrupted, like maybe we open it and we remove some of the chemicals, the remaining chemicals will reestablish equilibrium if we close that system again. So chemicals could be removed in a disruption. For example, if a chemical in an aqueous equilibrium is precipitated out or if it evaporates. But for a system to be at equilibrium, it has to be closed at a constant temperature to give us the constant macroscopic properties. And the intent is to hold the amount of matter and energy that are within the system constant, okay? The world is actually full of closed systems at constant temperatures where nothing appears to be happening. And equilibrium exists in a small percentage of those systems, but what chemists like to do is they like to poke systems to see if they're, let's say, alive. And we do this by changing certain things. So we may have a change in temperature. Maybe we increase the temperature. Maybe we decrease it to see if the equilibrium will reveal itself by causing some sort of a change or a shift in the amount of product or reactant that's present. If we restore the original temperature, then the original amounts should be restored and the equilibrium should shift back. Okay, if the reaction is photoactivated, like if it responds to a change in light, then we may observe that as well. So let's take a look at this quick check here. It says, why are chemical equilibria referred to as dynamic? That's because the forward and the reverse reactions continue to occur. Number 2 lists 3 criteria that have to be satisfied for chemical equilibrium to exist. Number 1, we have to have constant macroscopic properties. Number 2, we have to have a closed system. Number 3, we have to change conditions and see a shift in equilibrium. Number 3, what is a closed system? Closed systems are where no chemicals can enter or leave the system. Number 4, what is a macroscopic property? That's a property that's large enough to be measured or observed with the unaided eye. Let's talk about how equilibrium is established. So, as a reaction proceeds, reactant concentrations fall as reactants are consumed, okay? And the forward reaction rate of a reaction is going to decrease as we're consuming the reactant that's present. If we're in a closed system, the product concentration rises at the same rate that the reactant concentrations are falling, so the reverse rate is going to start to increase. And this continues until the forward rate and the reverse reaction rate are equal, and that's when you have equilibrium established. So this is showing you the 3 different stages that I just described. As the reaction begins, you have a high concentration of reactants. You had a fast forward reaction rate initially. Stage 2 is when the reactant concentration starts to fall. That means the forward rate is going to be decreasing. That's why this arrow going in the forward direction is slightly shorter. Meanwhile, since I now have some product produced, the reverse reaction rate begins to rise in this closed system with the product concentration coming up. And then stage 3, we're going to have the reverse rate equaling the forward rate. That's why those arrows are the same length. And we establish equilibrium. Now, how does this look on a graph? This figure here shows equilibrium is achieved when each one of these curves is steady. So at about 7 seconds, you'll notice that each one of these is steady, and that this top line is for the concentration of AB. This bottom line is for the concentrations of A and B. So you'll notice that initially I start out with no product. That's why this curve is rising up from 0. And then initially I have a higher concentration of reactants A and B, and it's getting consumed over time, which is why it's decreasing. Then eventually it levels off. So when the reactant and product concentrations become constant, that's when you have these lines being steady, and that is when you hit equilibrium, okay? So equilibrium is achieved around a time of 7 seconds. Let's take a look at the quick check just underneath. Are these questions true or false? Number 1, the reactant concentration always equals the product concentration at equilibrium. That is false. The concentrations of reactants and products will be constant, not necessarily equal at equilibrium. Number 2, when approaching equilibrium, the reactant concentration decreases while the product concentration increases. True. 3, the reactant concentration holds steady at equilibrium. That's true. 4, before achieving equilibrium, the forward rate is less than the reverse rate. False.